Okay, Chemistry 3101. We left off looking at chemical shift, and I said that we were going to tackle this question today, 15.10. But before we do that, let's review chemical shifts. And I'm going to give you a version or allow you to bring in a version of this table, which is posted to Canvas for quiz 15. You're not allowed to use it for the final exam, however. And so it's a good idea to familiarize yourself with these. When it says ppm values, that's another way of saying chemical shift. So chemical shift values of these common types of protons. So chemical shift is reported in parts per million. If you remember, chemical shift was actually a unitless number, but it's reported to times 10 to the negative 6. So we say it's parts per million. Anyhow, so with that in mind, some other points that you want to remember are that the more deshielded a proton is, the higher the chemical shift. Okay. Now, how do you get deshielding? Well, deshielding comes from removing electron density from around that proton. So what removes electron density? It would be something that's electronegative a lot of times. And so if you go all the way back, so if I just back up quite a bit here in the slides to when I first introduced the topic of chemical shift, you see that the baseline for a the baseline for methane, which is the simplest organic molecule in the universe, okay, if I circle it here in blue, is 1.0. But you see that as you add electron withdrawing groups like an iodine or a bromine or a chlorine or a fluorine, what do you see that happens to the chemical shift? It gets higher. It goes from 1 to 2.2 to 2.7. And it keeps increasing as you add more electronegative elements. And you know that fluorine is the most electronegative of all the halogens. We also see that the effect is additive, right? If we take chloromethane, this compound here, which has a chemical shift of 3.1, if you add another chlorine, it increases the chemical shift to 5.3. If you add another chlorine, it increases the chemical shift by even more. Now, not only do we see this effect with halogens, we also see it with oxygen. But before we can get into oxygen, we have to look at the baseline or the lowest possible chemical shift usually that we would see for a methyl, a methylene, or a methyne. And so you want to commit these numbers to memory. That a methyl, its baseline, what I call the baseline or the lowest chemical shift, would be about 0.9. Any electron withdrawing group is going to cause it to have a higher chemical shift than that. If you have a methylene, its baseline is 1.2, and for a methyne, it's 1.7. Then I said it would be wise to familiarize yourself with table 15.1, which shows you the effect of an oxygen from an alcohol or an ether. And we said that that has an electron withdrawing effect of 2.5 parts per million, or it increases the chemical shift by 2.5 parts per million. Again, if it's alpha to the oxygen of an alcohol or an ether. Then we said if you have an oxygen, or sorry, protons that are alpha or next door to the oxygen of an ester, that increases the chemical shift by what? 3 parts per million. And if you're wondering what these numbers are here, I said that if they're beta protons, it has 1/5 of the effect. And the last one is if your protons are alpha to a carbonyl group. In that case, the electron withdrawing effect causes an increase in the chemical shift by 1 part per million. If it's beta, it's 1/5 of that, which is 0.2. So we went over that last class. And I guess kind of where we left was right here with table 15.2. And so we've already looked at a methyl, a methylene, and a methyne again this morning, 0.9, 1.2, and 1.7. And notice that there's this little squiggle here. This means approximately. So you have to kind of take these numbers with a grain of salt. Next is allylic and vinylic. Okay, I know they're not next to each other, but I want to take a look at allylic protons and vinylic protons. So vinylic protons are protons that are attached directly to the carbon of a double bond. And we see that they have a chemical shift of 4.5 to 6.5 parts per million. And then you might think, well, if I have an aryl proton, right, that's attached to the carbon that's in a double bond, that should be 4.5 to 6.5 as well. But you see that the chemical shift is actually higher, and that's because of diamagnetic anisotropy that we took a look at last class. So the allylic proton, if you look at the carbon of a double bond, then go 1 carbon away. Protons that are attached to that are going to have a chemical shift of around 2. Then we said alkyl halides. We saw that again this morning. They actually have a wide range of chemical shifts, anywhere from 2 to 4. And that's because we have, iodine, bromine, chlorine, fluorine, right? And these have different electronegativities. Alcohols also have a wide range of chemical shifts, and we'll talk about alcohols a little bit more later on. Alkynyl protons, so if you have an alkyne, that's going to have a chemical shift of around 2.5. An aldehyde is really high, it's around 10. A carboxylic acid proton is at 12. And then the last one that's on here is an aromatic methyl, which is around 2.5. So again, it would be wise to commit these numbers to memory. So if I ask you a question like this, or if you're faced with a question like this on an exam in organic chemistry, you have to have an idea of how to use those chemical shifts. So it says here, use tables 15.1 and 15.2 together to help us determine the expected chemical shift for each type of proton in the following compounds. Now, something that we did last Thursday is that we identified all the different types of protons. Here you see them in the circles. So there's a total of what? 1, 2, 3, 4, 5, 6, 7 different types of protons in this compound. And where we started off was with the aldehyde proton. All right, if you go back in the table, it says that the chemical shift for an aldehyde proton is around 10. So what we'll do is we'll circle that proton. I have the red circle here, and we'll write a little arrow to it, and we'll put around or close to 10 parts per million would be the chemical shift of that aldehyde proton. All right, so let's keep moving on from there. So let's take a look at these protons here in this black circle. Well, those are methylene protons, right? A CH2 group. Now, what was the baseline for a CH2 group? So I'm going to use my black pen and put a line like this, okay? A CH2 group, its baseline was 1.2 parts per million. It was 1.2 parts per million. But keep in mind that this is, so yes, it would be 1.2, but this is not just a plain old methylene. Sorry, I forgot that here, this is vinylic, so these are allylic. So I'm going to put here allylic. So that would be 2 parts per million, 2 parts per million for the allylic. Plus, we have the electron withdrawing carbonyl group here, okay? And what was the effect of a carbonyl? If we're alpha to a carbonyl, could anybody tell me how much I should add to that 2 parts per million? If I'm alpha to a carbonyl, could anybody tell me how many parts per million should I add to that? So not 2.5. So if I go back here, if you're alpha to a carbonyl, so let's go all the way back here. Okay, when I'm alpha to a carbonyl, I add 1. Okay, it's 2.5 for an alcohol. Okay, so we'll go back here and we'll add 1 to that. So we'll say 2 parts per million for the allylic methylene plus 1 part per million. So that gives us around 3 parts per million. That's for those methylene protons. All right, so let's keep going. The next one, these ones are vinylic protons. So I'll use my red pen again here. So this is a vinylic proton. So this is vinylic. And if you look at the chemical shift for vinylic protons, it's 4.5 to 6.5 parts per million. If you're not sure where I'm getting that number, just go over here. Vinylic protons, 4.5 to 6.5. Now, something I would add to this, I actually looked at the solutions manual for this one. And in the solutions manual, it says this. It just says 4.5 to 6.5. So I would accept it if he says it's okay. But one thing I would add to that, though, is that it is, if this is the alpha carbon, alpha to the carbonyl, right, this is beta to it. And so if it's beta, then you could add 1/5 of 1, which is 0.2. So if you add 0.2 to 4.5, you get 4.7. If you add 0.2 to 6.5, you get 6.7. And so I would also accept 4.7 to 6.7 parts per million. But I mean, they're so close. It's fine either way. Okay, they're both perfectly acceptable answers. All right, the next one, the one in blue, those are vinylic protons, or that is a vinylic proton. So I'll put here vinylic like that. And vinylic protons, they're not beta to anything. They're not alpha to anything. And so for this one, we'll just put vinylic 4.5 to 6.5 parts per million. And again, this is all approximate. Okay, this is just our best guess. These ones, the green ones, are allylic protons, right? Again, we have the carbon of a double bond. Then you go to the next carbon, the protons attached to it. Those are allylic protons. So we'll put here allylic. All right. And so allylic protons, you can see, again, these are alpha or beta to any electron withdrawing group. So these are going to have a chemical shift of about 2 parts per million. The next one, the next methylene, the one in yellow. So this is just a CH2 group, okay? It's not allylic, it's not vinylic, it's nothing special. And so the baseline of that is just going to be 1.2. So I'll put here around 1.2 parts per million. And then the last one is an alkynyl proton. So from a terminal alkyne. So if we go back to the table, okay, we have terminal alkyne. So we call those alkynyl protons. They have a chemical shift of around 2.5. So we'll put here alkynyl. It's going to have a chemical shift of around 2.5 parts per million. And there we go. So we figured out the chemical shift of everything in here. And again, these are all just approximations. Are they going to be exactly at 2.5 and 1.2 and 2? No, okay. You know, it might have a little higher chemical shift. It might be a little bit lower, but these are good, you know, good expectations, okay? So if you want to predict what the NMR should look like, it should look something like this, or we should have signals in these areas. Again, you know, for this one here, you know, whether you put 4.5 to 6.5 or 4.7 to 6.7, I mean, the numbers are so close that I wouldn't stress about, you know, one or the other. They're both totally acceptable. These are just approximations, okay? All right, let's take a look at the one on the bottom. So first we'll start with the two protons that are vinylic. So we have two vinylic protons here, and they are alpha or beta to the hydroxyl group. Notice we have a hydroxyl group here of an alcohol. And so if those are vinylic, what I'm going to do is I'm just going to circle both of them together like this. And we'll just say vinylic. And if they're vinylic protons, they're going to have a chemical shift of 4.5 to 6.5, 6.5 parts per million. All right. These ones here, the CH3 group, this methyl group, those are going to be allylic. So I'll put here allylic. And they aren't alpha or beta to the hydroxyl, so they're going to have a chemical shift of around 2.5 parts per million. Okay, now what about these protons here in red? Okay, so if I put an arrow to these, so these ones are allylic. There's no doubt about that. Allylic, which would be 2 parts per million. Okay, would be their yeah. Did I put 2.5 there when I meant to put 2? Sorry, my mistake. So allylic protons, again, around 2.2 parts per million, not 2.5, around 2. Okay, so going back to the ones in red, the chemical shift, 2 parts per million. But what else would you say about these two protons? So if I highlight this one in yellow, would you say that's alpha to the oxygen of the alcohol or beta to it? Could anybody tell me that? And you can just write in A or B in the chat or unmute your mic. Either way is fine. Are those alpha to the alcohol or beta to the alcohol? Could anybody answer that? Yeah, they're beta. Exactly. So if they're beta, right, Jenny, if we go back to the table, so there's a lot of scrolling here. If we go back to the table, we said that the electron withdrawing effect of an alcohol was 2.5 parts per million. That's if you're alpha to them. But since they're beta, you add 1/5 of that. 1/5 of 2.5 is 0.5. So we're going to say 2 parts per million, and we're going to add 0.5 parts per million, and we get a total of 2.5 parts per million, like that. Now, what about the blue ones? Okay, the blue ones are just a methylene. Okay, they're not allylic protons, they're not vinylic protons. So remember, the baseline for a methylene was 1.2 parts per million, but these ones are alpha to the oxygen of the alcohol. So we're going to add how much? Could anybody tell me? How much are we going to add to the 1.2 to calculate our expected or anticipated, estimated chemical shift? If they're alpha to the oxygen of an alcohol, how much should I add? Could anybody answer that? It's going to have an electron withdrawing effect. By how much? So it's not 3. So if it's an alcohol, it's 2.5. So if we go back to the table, okay, if we go back here to the table, when it's an alcohol, the effect is 2.5. If it's an oxygen of an ester, then it's going to be 3. But when it's an alcohol, it's only 2.5. Yeah, 2.5. So we're going to take the 1.2 and then we're going to add 2.5 to that, and we get a total of 3.7 parts per million for that one. Then the last one is the alcohol, and we saw that alcohols have a wide range of chemical shift. It's anywhere between 2 and 5 parts per million. So we'll put here 2 to 5 parts per million. Another thing that we're going to see today is that the proton of an alcohol is usually not split. So it's usually a broad singlet. Okay, it's a singlet, meaning it just gives you one peak. Okay, so but it kind of looks like this. It's usually kind of broadened out. Anyhow, we'll talk about that later on in the lecture. All right, give me a thumbs up if you're with me. Does everybody follow at least a bit of the concept of chemical shift? That different types of protons in different environments next to electron withdrawing groups, right? They're going to have different chemical shifts. And this is a good thing, right? Because if all of these protons resonated at the same frequency, they'd all have the same chemical shift, then you wouldn't be able to tell them apart using NMR, and NMR would be a useless tool. But since the protons that are in different chemical environments or different electronic environments resonate at different frequencies, we can plot that, we get different chemical shifts, and that way we can differentiate between the compounds using an NMR spectrometer. So if you go back to kind of the last 20 minutes of Thursday's class, I said we were going to talk about three things, okay? Today, we were going to talk about chemical shift, and we talked about that a lot on Thursday. So chemical shift, so we've covered that, okay? And we're not done looking at it. Then I said that today we're also going to cover the topic of integration. Okay, so that's what we're going to be on right now is integration. And then after that, we're going to talk about what's called splitting or coupling. Either one is fine, okay? Coupling. And that's going to lead us to something called the N+1 rule. These are the three major topics that we're going to cover today. And again, we're not done with chemical shift. We're going to keep looking at it, okay? So now that we have an idea about chemical shift, okay, different protons are going to have different chemical shifts. It means their number in parts per million is going to be different because they resonate at different frequencies, right? If you go back to the whole idea of energy is proportional to frequency, which is proportional to the magnetic field, okay? So we understand why protons resonate at different frequencies and all that kind of stuff. But now we're going to move on to some more information that we can get from our NMR spectrum, and that is integration. And it says here that the integration, which is the area under a peak, quantifies the relative number of protons giving rise to a signal. Notice there's a couple of important words here, but one that pops out of my mind is the word relative, okay? So if you get a relative number of protons, if it's just relative, it tells you that it's really just a ratio, okay? Or you could even just simplify it and say not an exact number of protons, okay? You could just say it is a ratio of the relative number of protons. So what happens is that the computer, whichever computer you're using to process your FID, your free induction decay, and give you your NMR spectrum, just like this one down here, it does a couple of things for you. It's going to calculate the area under each peak, and then it's also going to give you a number that represents that area. And again, it's just a relative number, and it'll also give you what's called a step curve. So there's a lot to unpack here, okay? So if you're not awake, just wake up for like 5 minutes, and if I explain it to you, if you pay attention for the next 5 minutes, I can almost promise that you'll understand everything that I'm saying, okay? So, right, if you think in layman's terms, all right, if you went up to somebody on the street and you said, what does a peak look like? They'd say, this is a peak, okay? You know, well, in NMR, we say the whole thing is a signal, okay, or a peak, okay? So when it says a peak, it means to take the whole thing together. So if we go back here, okay, there we go. Okay, so when we look at this entire signal here, we say that is a peak, okay? So we'll just say that's a peak. And what happens is there's an area under that peak. So if I draw a line, that was a pretty crappy line. If I draw a line like this, okay, under the peak, the whole thing, there's an area, okay? Now you could calculate it. The units aren't important, but there's an area under that curve, okay? Same thing here. We say that this is a curve or a peak. and there's an area under that peak as well, okay? Now, you and I do not have the time or the patience or the energy to calculate the relative area under those peaks, okay? I don't know about you, but I certainly don't. So the computer does it for you. Now, maybe I should have used a different color here because it's a different area. But you see that the area in blue, the computer spits a number out at you. It says 27.0. It says that's a relative area underneath that curve, okay? Then it spits out another number for the other curve, and it says 40.2. There is no such thing as 0.2 of a proton. That doesn't exist, okay? So these are relative numbers. It means the ratio of protons represented by all four of these signals. So there's a signal here, right? That's what we call triplet. There's a signal here. That's a singlet. There's a signal here, and there's a signal here. You see the relative numbers are 27.0 to 40.2 to 28.4 to 48.2. Again, there's no such thing as 42.2 protons. They have to be a whole number. But these are just ratios. So what we do is we divide each one of these numbers by the smallest number. Okay, so what's the smallest number out of these four numbers? The smallest number is 27. So if you divide each one of these by 27.0, divide this by 27.0, divide this by 27.0, divide this by 27.0. I'm going to write the numbers on the top. You get 1.00, 1.48, 1.05, and 1.56. Again, there is no such thing as 1.05 protons. There's no such thing as 1.56 protons, right? 1.5 protons doesn't exist. What did I say these numbers were? I said they were relative, okay? So what could I multiply these by to get approximate whole numbers? Could anybody tell me that? What number could I multiply all of these by to get relative, okay, close whole numbers? Could we do some math in our head here? What if I multiplied the whole thing by 2? Okay, then I would get 2. I'd get pretty close to 3. I'd get pretty close to 2, and I'd get pretty close to 3. Can we have 2 protons? Yes. Can we have 3 protons? Yes. So then that gives us a relative number of protons. Does it mean that this signal is exactly 2? This signal is exactly 3? Maybe yeah, maybe no. It depends. You'd have to look at the molecular formula. It could be 4 to 6 and 4 to 6. But give me a thumbs up if you're with me on the idea. It's a relative number of protons. And to get the exact number of protons, you'd have to have a molecular formula. Okay? So you guys know what a belt is? You put it in your pants and it helps hold them up. You've probably seen a belt before, okay? Anyhow, have you ever heard of suspenders? Okay, suspenders do the same function, but they're different, right? Suspenders can help hold your pants up as well. Well, this spectrum is a little bit funny in that it kind of has a belt and suspenders on it. Normally, you only wear one, right? You don't wear a belt and suspenders at the same time. But anyhow, and I'm being a little bit silly here, but not only did they give you the relative numbers, okay, the 27, the 40.2, and all that stuff, but they also gave you the step curves. So the step curves are these things here. This is a step curve, this is a step curve, this is a step curve, and this is a step curve. So if you're wondering, what the heck do these squiggly lines mean? It looks like spaghetti that somebody threw on a page. The way you use a step curve is this, okay, is you would get a ruler out. You grab my ruler here, my rich young ruler, and you draw a line on the step curve like this. Now that didn't work very well, but anyhow, you get my drift, okay? And you would draw a line here, okay, on the 2 flat portions of your step curve, okay? Then you take your ruler and you measure the distance between the 2 flat portions. Now, again, I'm way out of whack here. I don't know, maybe it looks like, I don't know, 1.65 or something like that. Let's say it's like 1.65 centimeters. And then if I do the same thing for this one, again, I would draw a line like this and like this. Okay, it's easier without the ruler. Where did my ruler go? Okay, then you do the same thing like this. You'd measure here and you'd get 2.65 maybe for this one. So 2.65. Okay, and you would use those measurements the same way. You would divide them both by 1.65 and you would get a relative number of protons. You can imagine that using a step curve since our quizzes are multiple choice, it's kind of hard for me to use a step curve because I'm not going to ask you to measure something on a screen. I mean, it's a little bit ridiculous, but that's how a step curve works. All right. So again, what I did on the last slide is I divided every single one of those numbers by the smallest number, 27.0, 27.0, again, and again. And the numbers that I got are the ones at the top here. And again, these are not precise numbers of protons, but they give you an idea. And so if you multiply everything by 2, you get these numbers, but these are close enough to 2, to 3, to 2, to 3. Okay, again, it's very close, okay, to the relative number of protons. Okay, give me a thumbs up if you're with me on the idea of integration and how it works, what a step curve is, and then what those numbers mean. Okay, so again, it's a relative number of protons. Well, something that you've got to keep in mind is that these are relative numbers. So let's say you ran a spectrum on this compound here. Okay, so if you need a little refresher, based on what we learned last week, there are 2 types of protons in this compound. Okay, we have these types of protons, the red protons, and then we have these blue types of protons. Why are there only 2 types? It's because we have an axis of symmetry here, right? Rotational symmetry. If you rotate that 180 degrees, you see that there's symmetry. And so we would say that the blue protons are homotopic, and the red protons are homotopic. So we'll say here, we'll say these ones homotopic, right? Because there's rotational symmetry, and these ones are homotopic. So what's the conclusion? There's only 2 types of protons on here. Okay, so that means we're only going to see 2 signals in this NMR spectrum. We're going to see 2 signals. Now, if you have these 2 signals, okay, the red protons are going to be more deshielded because they're next to the carbonyl. So if you look at those, you have a baseline of 1.2, then you add 1. So they'd have a chemical shift of around 2. So we'd see the red protons at about 2.2 parts per million. And then we'd see the blue protons. What would they be? They'd be 0.9 plus they'd be 0.9 plus a fifth of 1, so that would be 0.2, so they'd be around 1.1, okay? Now, this is not accurate splitting, okay? We'd actually see a quartet and a triplet for these, but that's something that we're going to look at later on, okay? Now, but the relative integration that you would get for these, for the blue protons would be 3, and for these ones, for the methylenes, would be 2. But when you get those numbers for your integration, is there actually a total of 5 protons in the molecule? No, there's 10 protons in this molecule, right? The formula is C5H10O. But if you knew there were 10 protons, then you would say, well, these aren't right. You would say this must be a 4 and this must be a 6, right? Because 4 and 6 add up to 10. Okay, does that make some sense to everybody? It's just kind of more yammering on about the concept that we just looked at. We just get a relative number, but to figure out the exact number of protons, we need to have a molecular formula. All right, so here's the example of that compound. Okay, so one of the chemical shifts, like I said, was around 1.1, and the other one is around, this one looks like it's about 2.4 something. Okay, so, and like I said, there's a quartet and a triplet. But again, if you divide both of these numbers by 32, 32.5, and divide this by 32.5, I went ahead and did that already, you end up with 1.00 and 1.48. Well, 1.48 is not a whole number. If you multiply the whole thing by 2, then you get 2 and 3. Well, is the ratio 2 to 3? That's the ratio, but the actual number is 4 to 6. Does that make sense? Give me a thumbs up if this makes sense. Right, the number that the computer is giving us, yes, is 2 to 3. Okay, but the actual number is 4 to 6, and we need the molecular formula for that. Okay, cool. All right, so what we're going to do is we're going to try a problem here, and it just says you have a compound. The molecular formula is given to you. It's C10H10O, and it says determine the number of protons giving rise to each signal. So let's take a look here. So yeah, I already did the math on this one. I just want to be doubly sure, but I'll check it. So if you need it, I would recommend using a calculator for this. So what's our strategy? We have a total of 4 signals, okay? we have a signal here. We have a signal here, okay? And then there's another one really close to it, which is this one here. And then we have a signal here. Okay, so there's a total of 10 protons in this compound. So what we're going to do is we're going to look at the relative integration, 17.1, 87.1, 18.7, and 51.1. And now what we're going to do is we're going to divide all of them by the smallest number. So we're going to divide this by 17.1, do it here. So I'll just put 87.1 divided by 17.1. And then 18.7 divided by 17.1. And then we've got this one divided by 17.1. So here we get a 1. For this one, we get close to a 5. For this one, we get close to a 1. And then for this one, we get close to a 3. Again, I'm just rounding the numbers off. But if you tally up 1 plus 5 plus 1 plus 3, what do you get? You get a total of 10. So that makes sense. So that means that this signal way out here represents what? It represents 1 proton. This multiplet here represents 5 protons. This one here represents 1 proton. And this guy here represents 3 protons. All right. Give me a thumbs up if you're with me on that, on how to solve a problem like this, to look for the relative number of protons. Okay, cool. Just a little bit of math, okay, involved. And we're not done with the idea or the concept of integration. So going back a couple of slides, I told you we were going to cover, where was it? Oh, I guess it all got deleted. But I said we were going to cover integration, chemical shift, and then the last concept with respect to information on our NMR spectrum is going to be multiplicity. But before we do that, I want to take a look at this one here. So it says you've got a compound that has this molecular formula, C4H6O2. It has the following NMR spectrum. Determine the number of protons giving rise to each signal. So we've got 18.92, 19.77, and 19.46. So we're going to divide everything by 18.92, divide by 18.92, and divide by 18.92. Okay, this one I'd say you don't even need a calculator for it. You can probably just figure it out in your head. Okay, but for the first one, we're going to get 1.00, 19.77 divided by 18.92. We get 1.04 for this one, and then if we take 19.46 divided by 18.92, we get 1.03. So 1.03. So what does the ratio look like to you guys? Could anybody tell me? What is the ratio if we have a total of 6 protons in our molecule? Could anybody tell me how many protons are represented? Thanks, Isaac. Exactly. So Isaac says it's 1 to 1 to 1. But if you tally up 1 plus 1 plus 1, that's 3 protons. So Isaac, what do I have to multiply the whole thing by to give me the correct number of protons? And it's not a trick question. Exactly, 2. Then I get 2 to 2 to 2. So that means that this signal represents 2 protons, this signal represents 2 protons, and this signal represents 2 protons. And there you have it, my friends, done. That's it. That's integration. Okay, so that's the crux of how integration works. All right, so far we've covered what? We've covered chemical shift, and that's that number in parts per million. Okay, and I told you that chemical shift doesn't change whether you're using a more powerful spectrometer or a weaker spectrometer. It doesn't matter. We covered chemical shift. Then we covered integration, and we looked at the numbers that are spit out for the area under the curve, and we also looked at step curves, and I kind of showed you very quickly how to use a step curve. And now we're going to look at multiplicity. And we're going to cover what's called the N+1 rule. Okay? So again, hear ye, hear the sound of my voice. You will never be asked to explain the N+1 rule. If you're a chemistry major, we might ask you that. but this is, organic chemistry for non-chemistry majors. And so you don't have to provide me with an explanation of the n+1 rule. You just have to know how to apply the n+1 rule. Am I going to explain the n+1 rule? Oh, you bet your Bobby socks I will. Okay, it's important that I explain it. But again, you will never be asked to write an essay or give me, provide an explanation for the n+1 rule. So let's take a look here and talk about multiplicity. So we've got chemical shift, we've got integration. Chemical shift tells us about the environment that the proton is in. Integration tells us about the relative numbers of protons represented by each signal. And multiplicity is the number of peaks in a given signal. So sometimes I'll call it splitting, sometimes I'll call it multiplicity. They both mean the same thing. And again, what I'm telling you is that one of the major things you want to take away from this, so I'll say multiplicity overview, I'm going to put here n+1 rule is one of the major things you got to take away from this. So before we can get deep into multiplicity, you have to understand the terminology of singlet. So if we have one peak, that's a singlet. If we have two close together, that's called a doublet. This is a triplet. Then we have a quartet. That's 4. 5 would be a quintet. 6 is a sextet. And 7 is a septet, right? If you have a septet, you really have to be very, careful. So you count 1, 2, 3, 4, 5, 6, 7. You have to look at them very carefully. Anyhow, before we get deep into multiplicity, another thing I'll just mention, which is going to come up, is something called a coupling constant. So coupling constant, which is also called a J value. Okay. The J value is the distance in between the individual peaks. So let's say you have a quartet, okay? You can see there are 1, 2, 3, 4 peaks in the quartet. Well, if you can, in my pen, I don't even think it's fine enough to do this, but if you can look at the distance between the actual peaks, okay, which is a very small number, but remember, the NMR spectrum is split up in frequency, in hertz, right? So the number in here, this is what we call the J value. Okay, that's what we call the coupling constant, or the J value, okay? And it's measured in hertz. So I'll put here in hertz. And it usually ranges from 0 to 20 hertz, okay? So coupling constant, or J value, is the actual distance, right? We just calculate it in hertz, and it's usually between 0 and 20. All right, so now that we've got that, take a deep breath, because we're going to get into multiplicity and see what kind of information we can get from multiplicity, which is extremely useful. So multiplicity, where does this doublet come from, and a triplet, and a quartet, and a singlet, and a sextet? Where do these things come from? Well, it results from the magnetic effects that protons have on each other, okay? So it turns out that protons that are next to the protons that we're interested in are going to have an effect on the environment, or on, that the proton is in. So if you take a look at these two protons, if this makes any sense, so A and B, it turns out that if you want to know the chemical shift of A, it's actually affected by B, because B is actually pretty close. You see that B is only 1, 2, 3 bonds away. So B is close enough that it has an effect on A. Now, what are the two possible? When the nuclei were subjected to a magnetic field, B0, that they could either align with the magnetic field. Remember that? They would align with the magnetic field, and we call that an alpha spin state. And if they aligned against them, if you remember us at the very beginning, right? We had the alpha spin state and the beta spin state. Cha? Who remembers that? It was at the very beginning of the chapter. Right, we said that when you subject the nuclei to a magnetic with the magnetic field, some of them are aligned against the magnetic field. So remember, when we have a sample of a molecule, okay, we're not just talking about one molecule. We're talking about huge numbers, right? You guys know what Avogadro's number is, 6.02 times 10 to the 23rd power, okay? So we're talking about gigantic numbers of molecules. These numbers that are so big, it's difficult for us to understand. So the probability tells us that if there's that many molecules, that we're going to have billions and trillions and gazillions of HBs. And so what kind of environment is HA in? Well, it turns out it's in two different environments, because some of the HB protons are going to be aligned with the magnetic field, and some of them are going to be aligned against the magnetic field. So what does that mean? It means that HA is going to feel more of the magnetic field in some circumstances and less of the externally applied magnetic field in others. So it's in two different magnetic environments. And so one is going to have a higher chemical shift and one is going to have a lower chemical shift. And so it gets split. We say it's split into two peaks, okay, for our overall signal. And so we get a doublet. This is the N+1 rule. So the N+1 rule is neighbors plus 1. So if we look at HA, how many protons are next door or are neighbors to HA? The answer is 1. So what's 1 plus 1? 1 plus 1 is 2. And so that is why we get a doublet. Okay? Now, what if you have two neighbors? Well, based off of the rationale, what would I see for HA? I would see N+1. So I'd see neighbors. How many neighbors? It's got 2. 1, 2 HB protons. So I'd say 2 plus 1, which gives me 3, which would mean a triplet. And lo and behold, if you look at HA, it actually appears as a triplet. Now, what's the explanation for it? The explanation is, if it's got 2 protons that are neighbors, there's 4 possible scenarios that we can have. We can have one scenario where both HBs are aligned against the magnetic field, one scenario where they're both aligned with the magnetic field. So that's 2 different electronic environments. And then the third one is in between, when one is aligned with and one is aligned against. But since there's 2 protons, I can have a situation where this one is aligned with, this one is against, and this one is against, and this one is with. And so there's twice as many scenarios here. And so I see a ratio of 1 to 2 to 1 for the relative peak height of my triplet. But the bottom line that you need to know is neighbors plus 1. 2 neighbors plus 1 gives you 3. And so we see a triplet for that proton. Now, what if we have 3 neighbors? Okay, if HA has 3 neighbors, we say N+1 would be equal to 3 plus 1, which would give you 4. And that would be a quartet. So lo and behold, if you look at HA, when it has 3 neighbors, you see a quartet. Well, where does that come from? It comes from 3 different possibilities. One scenario where all 3 HBs are aligned against the magnetic field. One where all 3 HBs are aligned with the magnetic field. You have a third scenario where 2 are aligned against and 1 is with, but there's 3 ways that can happen. Then you have a fourth one where 2 are aligned with and 1 against, but there's 3 ways that can happen as well. And so we see the relative heights are 1 to 3 to 3 to 1 based off of the probabilities of these 3 different scenarios. But again, I'm never going to ask you to write this down and show all this rationale. You need to know is neighbors plus 1. If I have 3 neighbors, 3 plus 1 gives me 4, so I get a quartet. Give me a thumbs up if you're even like 20% of the way with me on the N+1 rule. Neighbors, you look at the number of neighbors, and then you add 1, okay? Now, what constitutes a neighbor? Well, it turns out that there's 2 possibilities for neighbors that we're going to look at in just a second. But what table 15.3 shows us is how the multiplicity trend continues by analyzing the splitting pattern of a signal in the proton NMR. So you can determine the number of equivalent protons. So what we're also going to do is we're going to look at it backwards. When we look at a spectrum and we see a quartet, what we're going to say is, however many protons are represented by this, they are coupled next to, or they are split next to how many protons? They must be split by 3 protons, right? Because 4 comes from something plus 1. So if we subtract 1 from 4, we get 3. So that means that however many protons are causing this signal, they were split by a total of 3 protons. Now, again, we're going to practice that in order for you to understand it. So there you go. So that's what the N+1 rule is. But what I was getting at is that there's 3 key rules that you have to keep in mind when you're thinking about splitting, okay? The N+1 rule. Okay, so you can't just go around invoking the N+1 rule until you really understand these 3 rules. The first one is that if you have equivalent protons, meaning homotopic or enantiotopic, okay, they don't split each other because they're going to resonate at the same frequency. So if you have equivalent protons, they're not going to split each other at all. Okay. The next one is what constitutes a neighbor. There's two possibilities for neighbors. You can either be 2 bonds away, that constitutes a neighbor, or you can be 3 bonds away. That constitutes a neighbor. Once you get to 4 bonds away and more, so 1, 2, 3, 4, that doesn't count, okay? It's too far apart for splitting to be observed. There is such thing as long-range coupling, but it's something that we don't even touch on in this class, so don't worry about it one little bit, okay? It doesn't come up at all in this class. And the last one is this. It says the n+1 rule only applies when protons are all equivalent. So what does that mean, okay? It means that you have to have protons that all have the same coupling constant in order for the n+1 rule to be applied. So when it says they're all equivalent, another way to put that is same, already here, same J value. And if you're like, Mr. Dion, I don't even know what a J value really is yet. Well, let me show you with this example here, okay? If we follow the n+1 rule for this proton in red, okay, it's a nice proton. Does it have neighbors? Yes, it's got 2 neighbors. Let's draw them in, right? This carbon has no protons on it, but this carbon here has a proton, doesn't it, right? It's got a proton in the back, okay? And then this carbon here has a proton on it too, right? It's this vinylic proton. Now, let me ask you something. The proton in red, and sorry, maybe I should use a different color. I'll change it to, I don't know, I'll change it to green, okay? The proton in green and the proton in blue, and keep in mind, my friends, I never ask trick questions. I hate them. The proton in green and the proton in blue, are those 2 protons the same? Are they equivalent to each other? Are those 2 protons identical? Thanks, Lauren. Right, Lauren? It's a resounding no. They are obviously very different, right? One is next to it, is attached to the same carbon with an alcohol. It's attached to an sp3 hybridized carbon. The one in blue is attached to an sp2 hybridized carbon, right? So they are obviously not the same. And so you cannot apply the n+1 rule in this specific case, okay? The protons have to be equivalent. But before you get too stressed about it, just about everything that we look at in this class, we are going to be able to apply the n+1 rule. Now, a little bit more about this n+1 rule and this whole J value thing, which I told you is the distance between the actual peaks. So let me get I'll use my green pen for this. It's not the best font, but the next best color. But the distance between here, I said those are what we call J values or coupling constants. When protons are splitting each other, so when we're applying the n+1 rule, if the n+1 rule can be applied, the distance between the peaks of the protons that are splitting each other have to be the exact same. So that would mean the J values have to be equal to each other. Now, if you're like, I don't even know what a J value is, Mr. Dan, all I mean is this. If protons are splitting each other, if you're using the n+1 rule, the distance between the peaks, you see they're all the same. So if you had something, like let's say you had a quartet that looked like this, okay, that looked like this, okay, and this is me trying to have the same between all of them, and then you had a triplet that looked like this, okay, those are not splitting each other because the J value here is not the same as the J value here, right? Those are very different, okay? Now, if you're like, well, how do I get down and measure those? You don't have to. You can always eyeball it in this class, and you can tell. Because trust me, if I give you 2 protons that aren't splitting each other, I will make it abundantly clear, all right? Now, if you remember, we talked about field strength. We talked about things like a 300 megahertz spectrometer versus a 60 megahertz spectrometer. And I said, you guys ever go on Yelp and look at restaurants? We'll try it here. So we'll say 300 megahertz, we'll put $3 signs, okay, next to it. You guys know what I'm talking about? And yeah, and then on a 60 megahertz, we'll put $1 sign on it. Give me a thumbs up if you know what I'm talking about on the Yelp reviews. When you look up a restaurant, it tells you, good. Hannah, this is exactly what it's like, okay? So a 300 megahertz, expensive, okay? A 60 megahertz, not expensive at all, okay? Now, again, it's like having an old, awesome. I like Yelp too. So If you have a 300 megahertz and a 60 megahertz, do they both give you the information? Yep, they do. But remember that a 300 megahertz, right, you have a greater range of frequencies, okay? Whereas with the 60 megahertz, you have a smaller range of frequencies, right? Now remember that when you get the resonating frequency, you divide it by the operating frequency of the spectrometer. So the chemical shift doesn't change, but the relative Lauren, I'm trying to find the thumbs down here. I can't find it. They're an anger emoji here. Hold on, let me see here. Blah, blah, blah. I can't find it. It's the best I could do with that one there. Okay. Anyhow, but the bottom line is, do you still get the picture? Yes. But with a higher frequency spectrometer, you can have less distance between, like actual distance between your peaks. And so you get a clearer picture. So it's nothing more than this. This would be the spectrum run on a 60 megahertz spectrometer, and this would be the spectrum run on a 300 megahertz spectrometer. Right? Both of them give you the same information. You have a singlet, and then you have a quartet. But you see that on the 60 megahertz, they overlap, whereas here you get a much clearer picture, right? You get a better resolution. So that's why a higher field strength spectrometer or higher frequency spectrometer is better. Okay, it just gives you a cleaner spectrum. Anyhow, so again, if you have protons that are splitting each other, you're going to have your coupling constant. You see the little lines that I'm drawing here. You see that these are all equal. Well, if I said, are these two protons splitting each other? You would say no. Why? Because the J value here, the distance between the peaks here, is different than the distance between the peaks here. Okay, so that's how you figure it out. All right. So how do I know? You guys remember ethyl groups? Who remembers the lowly ethyl group? Right? You guys, I remember methyl groups and ethyl groups. So an ethyl group was what? It was when you had CH2, CH3. Give me a thumbs up if you remember an ethyl group. I'm sure you're like, Mr. Dion, I've named enough compounds that I know what an ethyl group is. I don't need your help. Okay. So this is an ethyl group here, right? This is CH2, CH3. It turns out that an ethyl group is actually very recognizable in an NMR spectrum. Why? Because you end up with a quartet and a triplet. Let's take a look. Okay, so if you're not paying attention, wake up. Check this out. If I look at these two protons, right, these methylene, those two protons are homotopic. Okay, they're chemically equivalent. If I use the n+1 rule, how many neighbors do they have? 3. So I have 3 plus 1, which gives me 4. And that is why I get a quartet. Right? I get 4 peaks. Look, 1, 2, 3, 4. But those 4 peaks, that quartet represents are produced by 2 protons. Okay, so it's 2 protons that give us the signal. So the relative area under the peak would be 2 protons, right? But since it's got 3 neighbors, we get a quartet. Now for the methyl group, for the CH3 group over here, its signal, if you calculate the area underneath, it represents 3 protons, right? This comes from the integration. But where does the triplet come from? Because if we use n+1, how many neighbors does it have? It has 2 neighbors, so 2 plus 1 gives you 3, and that's why we get a triplet. Okay? Give me a thumbs up if that makes some sense to you. Or does anybody have a question about that? We're going to practice it. Trust me, we are going to practice it. Okay? But that's the idea. So there are 3 alkyl groups that are quite recognizable in the NMR spectrum, and we test them heavily. Okay? The first one is an ethyl. So you need to know ethyl, okay, what that looks like, and we saw it on the previous slide. Then we also look at a tert-butyl. Then we also look at isopropyl. Okay, so these ones are here. Now you guys know what a tert-butyl group is, right? You covered butyl, isobutyl, sec-butyl, and tert-butyl. If you look at a tert-butyl group, if I highlight this carbon in blue, okay, that carbon has no protons on it. But all 9 of these protons, right? You have 3 plus 3 plus 3. All 9 of those protons are chemically equivalent. Why are they chemically equivalent? Because there's free rotation around this bond, right? And so there's no way to differentiate between those 9 protons. But if you look at their neighbor, which is the blue, there's 0 protons, no H's. And so if you have n plus 1, it equals 0 plus 1, which gives you 1. And so when you see a singlet, if you see a singlet that has an integration for 9 protons, that tells you that you've got a tert butyl. The last one is an isopropyl. So this is an isopropyl group here. Now, again, there's free rotation around this bond, so there's no way to differentiate between those 6 protons on the methyl, right? If you write an isopropyl maybe like this, it might be easier. CH3, CH3, and then you have the CH here, the methine here. There is free rotation around this bond, so there's no way to differentiate between those 6 methyl protons. But how many neighbors do they have? They have 1. So if I use the n plus 1 rule, neighbors plus 1, I get 1 plus 1, which gives me 2. Now the integration is going to be 6, right? It represents 6 protons, but I get a doublet. Okay, so if you have a doublet that integrates for 6 protons, you might have an isopropyl. Now, if I look at the methine, the CH, I do the same thing. I say neighbors plus 1. It's got 6 neighbors plus 1 gives me 7. So I get a septet. Now, the septet is really small, and it's really hard to see. And if you're like me, you can't see anything, okay? So instead of zooming in like this, okay, or getting a magnifying glass, the spectrometer does the work for you. So the spectrometer zooms in on it for you, okay? So this is a magnification. So magnified, okay? We actually have a word for it. We call it an expansion, okay? The spectrometer does an expansion for you. So you can clearly see that it's 1, 2, 3, 4, 5, 6, 7 peaks, okay? So we get, again, reviewing n plus 1. It's 6 neighbors plus 1, which gives us a total of 7. Give me a thumbs up if you're even 50% of the way with me on an ethyl group, a tert butyl, and an isopropyl. Cha? All right, cool. So I'm going to skip the part on complex splitting for now. I'm going to come back to it later on, but let's not worry about it yet, okay? Let me go over a couple more rules with you, and then we're going to look at this problem. So I literally have 2 slides left, and then we're going to take a look at those ones, okay? So it turns out that some protons don't split, okay? If you look at ethanol, which is this compound here, if I write down the whole Lewis structure, ethanol, which you guys probably know already, even though we haven't studied alcohols, you've seen ethanol a few times in the book, okay? So it turns out that if you look at this proton, the alcohol proton, if you follow n plus 1, you'd say 1, 2, 3. So it's got 2 neighbors, so you might think 2 plus 1 equals 3, so I should get a triplet. It turns out that this is not what happens, okay? Alcohols don't split. So we'll just put here, no splitting, therefore singlet. Okay, so for an alcohol, we get a singlet. So if I look at the spectrum of ethanol, I have a triplet here, I have a quartet here, and I have a singlet here. Well, this singlet must represent, so if I'll call this HA. This must represent HA. Okay, this must be the alcohol proton. Now, if you're wondering, well, why the heck is that? Okay, why the heck is that? It's because the hydroxyl proton is labile. It undergoes exchange with protons in the solvent. So if there's any trace amount of solvent, what happens is the proton ends up getting switched so fast that there's no way that you can't see any splitting because it happens so fast that it blurs, it causes splitting to not occur. And sorry, I'm really struggling with my words here. And then since it gets exchanged over and over, the shielding and deshielding causes it just to be broadened because sometimes it's shielded, sometimes it's deshielded, okay? So an alcohol proton just gives you a broad singlet. Now this one is not very broad, but it is a singlet. All right, so there we go. So now what we're gonna do is we're gonna take a look at a problem, which is this one here, okay? So we're gonna start with this guy here. So how many types of protons do I have? So I'm going to go a little faster here. We have a methyl group here. We have a methylene here. We have a methine, a CH here, and then we have two methyl groups here. Okay, now what we want to do here is it says for each of the following compounds, determine the multiplicity of each signal. When it says to give the multiplicity, all it's asking us to do is to apply the n+1 rule. How many peaks will I see? So for the red protons, so for this one here, I do n+1, and this is not a joke, okay? There's no trick questions. How many, based off of the rules, okay, how many neighbors do these protons have? Remember, to apply n+1, you either have to be on the same carbon or 1, 2, 3 bonds away from each other. That's the only time we apply the n+1 rule. N+1 rule. So do those three protons, thanks to Rubio, it has none, right? If you count, look, if we look at these three protons, we'll just highlight this one. We go 1, 2, 3, right? What's here? This is a carbon. And if I go 1, 2, 3 here, this is an oxygen. Those aren't protons. So these three protons, those three protons in that red circle, they're not split by anything. So we would say 0 plus 1 gives me 1, and therefore these are going to give me a singlet. All right.